Okay, this is the last method of volumes we're going to look at. It's the hardest to visualize, and I'll do my best to show you what's going on. But for the most part, you'll be told what to do, so there'll be very little guesswork. So let's jump right into an example. It says, here's a region. It's bound by the curve y equals the square root of x minus 3, that's the red curve, the x-axis, and the line x equals 12. Now here's the difference between this and what we've been doing. They tell you this is the base of a solid, so we're no longer rotating anything. We have a solid. This is the base of the solid. So I am in an airplane. I'm looking down on the solid, and this is what I see. I see the outline of the solid. It says cross sections perpendicular to the x-axis are equilateral triangles. So if I take any slice through this solid that's perpendicular to the x-axis, and I look at what I would see from the side, I would see an equilateral right triangle. We're asked to find the volume of the solid. Okay, before we get into the nuts and bolts of how to do this, let's take a look at what the solid actually looks like. Okay, so we're back in wind plot. Here's the curve in red. The barrier x equals 12 is in blue, and the x-axis serves as a boundary in turquoise. I'm going to ask wind plot to draw me the solid. Okay, and let me go ahead and put some axes on here. The curve determines the boundary of this solid, and now I'm looking at a ground level view of the solid, and I can see equilateral triangles that have different side lengths based on how high the curve was, at least from the curve down the x-axis. So you can see a bunch of equilateral triangles have been stacked on top of each other to create some volume. There's more or less the view of the curve in the xy plane, as if you were looking down at it from an airplane or from a hot air balloon or a blimp. And then again, if you're on the ground level, you would see cross sections that are equilateral triangles. Okay, so how are we going to go about doing this? Well, we're going to do what we've been doing, which is to draw a rectangle that represents one slice of this region, and we're going to ask ourselves, what role do the dimensions of this rectangle play in the overall dimensions of the solid here? Okay, so again, I'm going to draw generic coordinates on this rectangle, x comma 0, and x comma, in this case, the square root of x minus 3. I know that the width of this rectangle is arbitrary dx. Now, that strip, so I take that strip out, and it would look like an equilateral triangle that would have some width to it, which makes a triangular prism. And that width is our arbitrary dimension dx in this case. And now here the question is, what is the length of the side? Well, that's clearly going to be the distance from my boundary x comma 0 up to the curve x comma square root of x minus 3. So each side has the same length of square root of x minus 3. So now I have to look at this figure, this prism, and ask myself, what's the volume of the figure? Okay, so it's going to be the dx times the area of the face. And the area of the face of this figure is the face is an equilateral triangle, so I need to figure out what's the area of the equilateral triangle that has this side length. So without getting into too much detail, okay, if you have questions about this, you can email me, let me know. But the area of an equilateral triangle is the square root of 3 over 4 times the side squared. So I have the square root of x minus 3 as the side length. We're going to square that, and that'll be the area of the face times the dx, will give me a volume. So the volume of the whole solid now is going to be the integral of this formula. So I have the square root of 3 over 4 times x minus 3, because the square and the square root cancel, the dx, and my limits of integration are going to be from, in this case, 3 up to 12. So now all I have to do is evaluate the integral. Let's take out the square root of 3 over 4, which makes our calculation a little bit easier. I have x minus 3 dx to integrate, or to anti-differentiate. The antiderivative is going to be 1/2 x squared minus 3x from 0 to 12. And as always, I want to put two big parentheses with a subtraction sign. So I have square root of 3 over 4. I'm plugging in a 12. I'm going to get 144 over 2, which is 72 minus 36. And over here, I misspoke. I should not have put a 0 there. I should put a 3 there. And so now we're going to get square root of 3 over 4 times 9/2 minus 9. Now to clean all this up, we know there's a square root of 3 over 4 common to both parentheses. This is a 36 in the first quantity, minus, let's see here, 9/2 minus 18 halves would be negative 9 halves, which is a plus. So a plus 9 halves, and that becomes 72 halves plus 9 halves. That's 81 halves. So the square root of 3 over 4 times 81 over 2. And so we're going to end up with 81 square roots of 3 over 8. Okay, let's look at one more example, and then we'll leave one for you to do. It says the base of a solid is the region between the curve y equals 2 square root of sine x and the interval 0 to pi on the x-axis. Cross sections perpendicular to the x-axis are, again, equilateral triangles with bases running from the x-axis down to the curve. And here they give you a little bit of picture of what's going on here. You can see the equilateral triangles kind of popping out of the base of the region here. Gives you an idea of what's going on. Okay, so once again, you draw a rectangle in the region. This time I have to draw my rectangle a little bit sideways here. Okay, just to give yourself coordinates to work with here. So the coordinates at the top of the rectangle are x comma 2 square root of sine x, and the coordinates at the bottom of the rectangle are x comma 0, and dx is your width. Again, you're dealing with equilateral triangles, so each slice is going to produce a triangular prism with dimension dx here, and the side length is 2 times the square root of sine x. So the volume of this prism, once again, is the area of the face times dx, and from geometry, the area of an equilateral triangle is always going to be the square root of 3 over 4 times the side squared, so 2 square roots of sine x, quantity squared. So overall we have the square root of 3 over 4 times 4 sine x, the 4's will cancel, times your dx. And so to find the area of the entire region, to find the volume of the entire region, we want to integrate that formula from 0 to pi in this case. So we have the square root of 3 times the sine of x dx, the antiderivative of which is going to be negative square root of 3 cosine x from 0 to pi, 2 big parentheses with subtraction sign. So we have negative square root of 3 times the cosine of pi, and that gives us square root of 3, minus negative square root of 3 times the cosine of 0, so negative square root of 3, so overall we get a volume of 2 times the square root of 3. Now if you'd like to try one, this time in part B it says we use the same curve, the same region. This time the cross sections are squares with the bases running from the x-axis down to the curve. So this will be a slightly different calculation but related to what you just did. And if you'd like to run that answer by me to see if you're right, feel free.